Alright guys, welcome back. This is the second video, the second part of our notes today. This is notes over the Big Bang Theory and the evidence for the Big Bang Theory, specifically number 5 in the notes, stellar formation and stellar evolution. If you've not already watched part 1, you need to go back into Schoology and find part 1, because this is the second video where I'll build on that idea, okay? So, here we go. Stellar formation and stellar evolution, number 5. So in part 1 of this video, I talked about how we use telescopes, both Earth-based telescopes and space-based telescopes to view the night sky. And I talked quite a bit about a telescope that looks a lot like this one out near Lewisburg, which is the Powell Observatory. So this video, this part 2, I'm going to be talking about this diagram down here. All right, the life cycle of a star. And again, I'm not saying that stars are actually alive. They're not alive, but they go through this life cycle, this kind of evolution throughout the span of time that the star is actually a star. And so we call it a life cycle, okay? All right, so stars are born in these stellar nebulas. They're created in these stellar nebulas, and I'll explain that in a minute, but I'm just going to show you a few pictures of nebulas real quick. Okay, these are actual images. These are not drawings. These are not artists creating these. These are actual images. This first one here is called the Helix Nebula. It's one of my favorites. I love the Helix Nebula. It looks like a big eyeball staring at you. The Crab Nebula, which is a very popular, very well-known nebula. The Ring Nebula, which looks like a flower. It's beautiful. The very creepy, kind of ominous looking Horsehead Nebula here. And then, I don't know, here's a newer one that's been recently discovered called the Seagull Nebula. To me it looks like a dragon. Oh, so cool. My very favorite nebula is the Pleiades. Okay, it's called the Pleiades. It's known as the Seven Sisters. There's lots of folklore around the Pleiades. There's actually like 21 stars here. But to the naked eye, without a telescope, you can only see 7 of them. Some of them are too close together. Some of them are just not bright enough and are outshined by the others. So without a telescope, you see 7. One of the reasons this is my favorite is because you can see it without a telescope. You don't have to have a telescope to see this nebula and see this kind of like blue fuzz around it. When you see this in the night sky, it looks like a blue smudge. Like somebody smudged the sky around these, and it's really cool. You don't need a telescope. I encourage you to go outside and find the Pleiades on a clear night. It's really worth it. I love watching for it. But another reason I really like the Pleiades is because I'm a car guy. I've always kind of loved cars. I've loved learning about cars and the history and the racing and all that kind of stuff. And the Pleiades is involved in racing in the cars in the form of Subaru. Subaru, so in Japanese, the folklore around the Pleiades is that there are 7 sisters, but one of them is missing. Okay. Well, in the Subaru logo, there's 6 stars. All right. And the name Subaru is the name for the Pleiades in Japanese. So it's the whole car naming and logo is based on this star formation right here, which is really cool. So these are the places where stars are born. And you can really kind of see it here. Look at all these stars. There's a bunch of them. And if you look inside the nebula, the stars are being created in here. They're being born inside the nebula itself. And the reason for that is because there's lots of stuff. There are particles, lots of particles, and heavy particles, not just hydrogen and helium, but there's lithium and beryllium and boron and carbon and oxygen, and all the way up through element number 26, which is iron, which is all the stuff that stars make throughout the normal life cycle. But then inside these nebulas, it continues on, and you have iron and lead and bismuth and uranium and plutonium, and you have just all the rest of the elements on the periodic table. They're all here. There's gold, silver, platinum, aluminum, It's all here inside these nebulas, okay? And because all these atoms have a mass, they weigh something, they have a mass, they have gravity. And so over time, these particles start pulling together in clumps. And as they pull together in clumps, their gravity increases. And the pressure inside on the very center ones start to increase. Okay. As the gravity increases from the outside, smashing in on the star, okay, gravity gets bigger and bigger and bigger. At some point, right here in the center, the very two center atoms, which are probably hydrogen, because the universe is mostly hydrogen, the very two center atoms are going to be pressed together so incredibly hard that the nucleus, fuse together. They come together and fuse together in a process that we call nuclear fusion. Well, once that nuclear fusion starts, there's a burst of energy given off. And that energy given off pushes outward against the gravity. And the star reaches what we call equilibrium. The same amount of pressure pushing in, the amount of pressure squishing in due to gravity is the exact same as the amount of pressure pushing out. If the amount of gravity pushing in was greater than the amount of gravity pressing outwards, well, the star would just collapse and get smaller until the pressures are the same. If the star has more pressure on the inside pushing out than on the outside pushing in, the star would expand, and it would expand until it reaches equilibrium or explodes or whatever. So your body right now is in equilibrium, more or less. Okay? The pressure pushing in on or down on you, inwards on your body in all directions from atmospheric pressure and gravity, is equal to the amount of pressure on the inside of your body pressing back out. And just like the star, if the pressure on the outside was greater, you would be crushed. If the pressure on the inside would be greater, you'd swell up. When you twist your ankle, you break a blood vessel or whatever happens. I'm not an anatomy guy, but whatever happens when you twist an ankle, there's fluid built up in your ankle, and it swells because there's more stuff there pressing outwards. Your skin swells a little bit. Now, technically, you have a little higher pressure inside your body than on the outside because when you poke a hole in yourself, you bleed. The blood is forced out. That forcing out is because the pressure on the inside is a little bit greater. Okay. A great example of this, you probably didn't think when you came to science class today that you'd be talking about blobfish, but a great example of this is the blobfish, which is a deep sea ocean fish. They live down very deep in the ocean. I don't know, 2 miles. I'm making that up. I don't know how deep, but we're going to pretend it's 2 miles. Deep. That's the point. Blobfish live deep in the ocean, and if it's 2 miles down, imagine 2 miles of water on top of you. Your body would be crushed. It's kind of hard to imagine what 2 miles of water would look like, but and how much weight that would be. But 1 gallon of water weighs 8 pounds. So imagine what it would be like to fill up enough milk jugs to stack on top of each other to go 2 miles, and then to lay underneath that. Okay, that's how much water it would be. It would crush you. You'd just be smashed. It's a lot of water. That amount of water doesn't crush these fish because they have enough pressure on the inside pushing back out that they keep their shape. In fact, they require this amount of pressure. They can't survive in shallow water. You don't see blobfish at aquariums. You can't go to the pet store and buy one. When you do bring a blobfish, let's say a blobfish is caught in a net or on a hook and line, I don't know how you would catch one, but they have been caught and brought to the surface occasionally. And when you catch a blobfish and you bring it to the surface, it looks like this. This is a blobfish brought to the surface. Now you can see why they call it a blobfish. It looks like a blob. This is like some fatty, slimy blob. But down in the ocean, it doesn't look like that at all. The reason it looks like this is because it died a very painful death. The blood vessels inside of its body burst. Its organs burst. And it just kind of expanded until it stretched out into this weird, nasty, slimy looking blob. It's actually pretty sad to think about. I mean, to go from this to that. But it's all the same process. The outward pressure and the inward pressure have to be equal or bad things happen. Okay? And bad things would happen to you if you went down where the blobfish lived, because our bodies aren't designed to live in places of high pressure, right? So stars are the same way. And stars in this stellar nebula are born here. And if there's enough stuff for fusion process to start, most stars come up in this upper life cycle up here, the average star. Our sun, is an average star. There's nothing really that special about our star. It's not too big, not too hot. You know, it's just kind of average, not too bright. Our star is fusing hydrogen and helium, or hydrogen into helium, 2 hydrogen atoms into helium. Eventually it'll run out of hydrogen and it'll start fusing helium into lithium, and then lithium into beryllium, and it'll continue up to element number 26. Each time that it moves up, oops, hold on, going the wrong way. Each time that it fuses something together, it gives off a little bit of energy. It's converting mass into energy. E equals mc squared. Just like the Big Bang converted energy into matter, this is kind of going the other way. It's converting matter back into energy in the form of light and heat and ultraviolet and X-ray and radio waves and gamma rays and everything else. And so what's going to happen is it's going to be giving off a little bit more energy, and it's going to be losing, it's going to be losing a little bit of gravity. It's losing a little bit of mass. As it loses its gravity, just like the blobfish, it's going to start to swell. All right, it's going to swell up. It's going to swell, and it's going to start running out of gravity. First, it's going to swell up a little bit, and it's going to slowly start to turn red because the same amount of energy is being given off, but in a wider area and a bigger volume. So it's going to start to turn red. And it's going to swell up, and it's going to swallow up Mercury. Mercury will be gone. Mercury will burn up inside of the sun. And then the sun will continue to expand up to about the size of the orbit of Venus. And Venus will be gone. It won't exist anymore. It'll be burnt up. And then it will continue to expand to the orbit of Earth. And Earth will be burnt up, and Earth will be gone. No more Earth. And it will continue to expand, and it'll expand almost to the edge, like almost touching Mars. And that's about where it's going to stop. Now, we have a long time. It's not going to happen for about 5 billion years, but this is going to happen. We're fairly confident because we can see other stars doing this. It's going to swallow up Mercury, Venus, and Earth. Our moon will be gone. Our planet will be gone. Hopefully, if humans are still around, we figured out how to get off Earth, because that's going to be a bad day. And then it's going to suddenly run out of energy. When it reaches element number 26, when it fuses its last, whatever element number 25 is, I don't know off the top of my head. Whenever it fuses the last number 25 into 26, the pressure outward stops giving off energy. But the gravity is still there. And it will instantly collapse. Boom, it'll collapse. And it'll be sort of like pulling a rug out, or a tablecloth out from underneath the dishes. The dishes still stay in place. Well, what happens is a little bit of the outer edge of the sun, the outer layers, are going to continue being out there. But most of the star is going to collapse into the center, into a white dwarf. Oof, and I'm out of time. I'm going to have to make a third video. So go find the third video on Schoology. Sorry, guys. Go find the third video on Schoology.